Welcome to the fourth week of this course. By now, you've seen forward propagation and back propagation in the context of a neural network with a single hidden layer, as well as logistic regression. And you've learned about vectorization and when it's important to initialize the weights randomly. If you've done the past couple of weeks' homeworks, you've also implemented and seen some of these ideas work for yourself. So by now, you've actually seen most of the ideas you need to implement a deep neural network. What we're going to do in this week is take those ideas and put them together so that you'll be able to implement your own deep neural network. Because this week's programming exercise is longer and just has a bit more work, I'm going to keep the videos for this week shorter so you can get through the videos a little bit more quickly and then have more time to do a significant programming exercise at the end, which I hope will leave you having built a deep neural network that you feel proud of. So what is a deep neural network? You've seen this picture for logistic regression, and you've also seen neural networks with a single hidden layer. So here's an example of a neural network with 2 hidden layers and a neural network with 5 hidden layers. We say that logistic regression is a very shallow model, whereas this model here is a much deeper model. And shallow versus depth is a matter of degree. So a neural network with a single hidden layer, this would be a 2-layer neural network. Remember, when we count layers in a neural network, we don't count the input layer, we just count the hidden layers as well as the output layer. So this would be a 2-layer neural network, is still quite shallow, but not as shallow as logistic regression. Technically, logistic regression is a 1-layer neural network. But over the last several years, the AI and the machine learning community has realized that there are functions that very deep neural networks can learn that shallower models are often unable to. Although for any given problem, it might be hard to predict in advance exactly how deep a neural network you would want. So it would be reasonable to try logistic regression, try 1 and then 2 hidden layers, and view the number of hidden layers as another hyperparameter that you could try a variety of values of and evaluate on Hodar cross validation data or on your development set. Say more about that later as well. Let's now go through the notation we'll use to describe deep neural networks. Here is a 1, 2, 3, 4-layer neural network with 3 hidden layers, and the number of units in these hidden layers are, I guess, 5, 5, 3, and then there's 1 output unit. So the notation we're going to use is going to use capital L to denote the number of layers in the network. So in this case, L is equal to 4. And so that's the number of layers. And we're going to use n superscript L to denote the number of nodes or the number of units in layer lowercase l. So if we index this, the input, as layer 0, this is layer 1, this is layer 2, this is layer 3, and this is layer 4, then we have that, for example, n1, that would be this, the first hidden layer, would be equal to 5 because we have 5 hidden units there. For this one, we have that n2, the number of units in the second hidden layer, is also equal to 5. N3 is equal to 3, and n4, which is n capital L, is the number of units, this number of output units is equal to 1, because here capital L is equal to 4. And we're also going to have here that for the input layer, n0 is just equal to nx is equal to 3. Okay, so that's the notation we'll use to describe the number of nodes we have in different layers. For each layer L, we're also going to use AL to denote the activations in layer L. So we'll see later that in forward propagation, you end up computing AL as the activation G applied to ZL, and perhaps the activation is indexed by the layer L as well. And then we'll use WL to denote the weights for computing the values ZL in layer L, and similarly BL is used to compute ZL. Finally, just to wrap up on the notation, the input features are called X, but X is also the activations of layer 0. So A0 is equal to X, and the activation of the final layer, A capital L, is equal to Y hat. So A superscript square bracket capital L is equal to the predicted output, the prediction Y hat of the neural network. So you now know what a deep neural network looks like, as was the notation we'll use to describe and to compute with deep networks. I know we've introduced a lot of notation in this video, but if you ever forget what some symbol means, we've also posted on the course website a notation sheet or a notation guide that you can use to look up what these different symbols means. Next, I'd like to describe what forward propagation in this type of network looks like. Let's go into the next video.